All right, good morning, friends. I hope you are having a good minor exam and not too stressed out. So the plan for today is to hopefully wrap up all of graph theory, and in the next lecture we'll start something completely new. In particular, we'll definitely try to wrap up the proof sequence business, and then maybe if time permits, I'll introduce you not in a very formal way to other types of graphs, multi-graphs, directed graphs, and so on, just so that you all are aware of these things. Okay, so the next lecture, first of all, announcements. Next lecture is going to happen on September 25, which is a buffer day, which is this Saturday. Next tutorial, as scheduled, it was September 23, but if you want to have some kind of a break for a day or two, I can consider shifting it to September 25. What do you guys think?
Yes, sir. Yes,
Yes,
sir.
sir,
Yes,
that
sir.
would be good.
Okay, cool.
Brilliant.
So let's make it September 25. September 25, could we have it immediately after class, 11 o'clock, let's say?
Yes, sir.
Unless you have some other
Yes,
commitments?
sir.
So actually, sir, that day I
No.
will be traveling in the evening to come to on boards. So at 11
So
o'clock will be
no,
very
no,
great
no.
actually.
That's not what I asked. So if in general some other class has
No,
been
no.
scheduled, right? Some other courses lecture has been scheduled. That is what I'm concerned about. So I cannot, unfortunately, I cannot address the issues of one student at a time, right?
Yeah, I understand.
Yeah. Okay. So September 25. Let's make it September 25, 11 to 12. Or maybe after lecture we could take a 5 to 10 minutes break and then rejoin. That's completely up to us, right? So I hope that day is kind of flexible for all of us. Okay, so we'll figure out. So tentatively, let's say 11 to 12. Okay, did I start? Yeah, I started recording. Okay, cool. So what did we do last time? The question we were asking is, let's say I give you a finite set S and I tell you to construct all possible trees with vertex set S. How many trees will you get, right? And then we tried this for some small sets, right? So I think for the size of set being at most 5, we did everything. 6 we didn't do, right? 6 we didn't try. For a size of S being equal to 6, we didn't try to explicitly enumerate all possible trees, but okay, fine. And then from whatever we observed, we conjectured that the number of trees over a finite set S of vertices is size of S to the power size of S minus 2. Okay, and then in order to prove that, we informally defined the notion of a prefer sequence of a tree, although we'll make it formal only today, right? So so given a tree, how do we construct a prefer sequence? So first of all, let's assume that the vertex set of the tree is a subset of natural numbers, uh, right? Okay. So all I'm trying to say is that there should be some well-defined order on the vertex set, right? So you fix a give given a tree and given a fixed order on the set of vertices, that allows you to kind of properly define the prefer sequence of that tree. So how do you define the prefer sequence? You find the leaf X with the minimum possible label according to whatever order you're looking at. You record its neighbor, okay, let's say Y, and then you delete the leaf and its neighbor XY, right? And then you recurse on the remaining tree. Okay, how long do you do that? Once you end up in a tree with just two vertices, which means it has just one edge, you stop. Okay, so in particular, if you started out with a tree with just two vertices, then your prefer sequence is empty. Okay, so is the construction of a prefer sequence clear to everybody? Raise your hand if it is not clear. Okay, cool. So yeah, so that construction seems to be clear. So why did we at all define the prefer sequence? If you recall, the idea was you have, let's say, trees over S, and you have another set of sequences over S of length size of S minus 2, right? And then we were hoping to show that there is a bijection between them. The size of this set, the number of elements of this set is obviously n to the n minus 2, or rather size of S to the size of S minus 2. right? And then if we establish this bijection, we have proved the claim, right? We have proved that the number of trees over S is size of S minus size of S minus size of S to the power size of S minus 2, right? So we wanted this bijection, and then this gives some function, right? So the prefer sequence, right? The function which maps a tree to its prefer sequence gives some function from this set to this set. And now it is our job to prove that it's a bijection. Okay, so I hope all of you remember this context. So last time we also tried to construct the prefer sequence of a specific tree as an example. I think we finished that, and then last time the other question I asked is, given, let's say I give you a set S and I give you a sequence of size equal to a sequence of length equal to size of S minus 2 over the set S, can you construct a tree whose prefer sequence is exactly this sequence? Okay, so we were trying to do that, and in that attempt we asked the question, what are the interesting properties that are kind of revealed by this prefer sequence immediately, in particular, right? So if this is the prefer sequence of some tree T, what are the leaves of tree, what are the leaves of T? Okay, so Shrimanti, you had a question, could you ask that question now?
Yes, sir. So I was saying that we know that leaf nodes cannot occur in the prefer sequence, but I'm saying that if there is a non-leaf node, but how can we ensure that there are no non-leaf nodes in this 3, 4, 6, 8 among this 3, 4, 6, 8?
Acha. Okay. Good. Yeah, fine. So what did we say? What did we say last time? We said that because 3, 4, 6, 8 do not appear in the sequence, right? So we claim that these must be the leaves. So one thing is clear, that a leaf will never appear. Yeah. So something that does not appear in this prefer sequence has to be a leaf. Is that clear, or is the other way clear? Shrimanti, which way is clear for you?
So it is clear that a leaf node cannot occur in the prefer sequence.
Okay. So it is clear that a leaf. Okay. So fine. So raise your hand if it is clear to you. Everybody, yeah, this is a question for everybody. Raise your hand if it is clear that a leaf node cannot appear in the prefer sequence. Okay. So it's clear to, I don't know, half the class. Oh, almost all of the class. Almost everybody who is present over here. Cool. Yeah. You can lower your hands now. And what is the brief justification for that? Right. So in order, so suppose this is a leaf node, let's call it L. Right. So in order for L to appear in this prefer sequence, you should be able to delete some node which is a label of L, which is a neighbor of L. Right. And only then you will record L into your prefer sequence. But then for that node to get deleted, what should happen? For that node to get deleted, at its time of deletion, that node should also be a leaf. What does that mean? So it means that at the time of deletion of this node X, the tree you're left with is just this tree. But then what did we say about the construction of the prefer sequence? As soon as just two vertices remain, we just stop, right? So which means that when you landed up in this situation, you should not have recorded L, you should have just stopped. Right, so which is why a leaf node cannot appear in a prefer sequence. Okay, and now the converse is, why is everything that does not appear in the prefer sequence a leaf node? Does somebody want to suggest some answer for this? Right, so if some vertex X does not appear in a prefer sequence, why is X necessarily a leaf node? Yes, Vedant?
So suppose there is a non-leaf node which is not in the sequence. So there must have been either a leaf attached to it, or it is or there is no leaf attached to it, right?
Okay.
Those are the only two cases. If there is a leaf attached to it, then at some point we may have removed that leaf, right?
I don't quite agree with this claim. Right, so if there is some leaf attached to it, but what if that leaf has the highest possible label?
But oh yeah, right. So it's not in the sequence, so we don't know that.
Yeah. Yeah. But you're almost there. You are almost there. You're almost there. Somebody, Ramanuj?
So I think we can generally prove that the number of appearances of a number in the proof of sequence will be equal to the degree of the number minus 1.
Okay, good. So what is the claim? The number of appearances of a vertex X in the prefer sequence is 1 less than the degree of X. And why is that so?
It's so because, for example, like if you have a number appearing twice, then you'll have deleted 3 numbers which were attached, 3 leaves or leaves at that point of time, which were attached to it. And also at the end, you cannot delete every line which was attached to it, because that would just create an isolated vertex. So there would be another line which is attached to it. And also you cannot do something like not delete one, like you can, the vertex cannot be left with 2 or more edges at the end, because if it's left with 2 or more edges, then we cannot have it like the 2 vertices.
I kind of get your idea. You're on the right track. Yes, Somil?
What I'm going to say is like almost similar to Ramu's. Like,
Achha.
so whenever you remove a leaf, so whenever you remove a leaf, then the leaf is removed and its neighbor, the degree of its neighbor is decreased by 1, and for all the other vertices, the degrees remain the same.
Correct.
And we know that finally every vertex is either removed or it remains in the last edge, in which its degree is 1. So let's say a vertex had degree d, then if it was removed, then its degree must have been decreased d minus 1 times before it was removed. So it must occur d minus 1 times. And if it remains in the tree at the end, like if it remains in the edge, then also its degree must have been decreased d minus 1 times.
Lovely argument. Okay, nice. Okay, so let me quickly repeat the argument. So Somil's argument is the following. So look at any vertex X, right? So there are 2 possibilities. Either X survives till the end, or X is deleted sometime during the construction of the prefer sequence. Okay, so let us consider these 2 cases one by one, or rather in both cases, right? So at the time of the delete, at the time X is deleted, or at the end of the sequence, if X survives till the end, in both of these situations, the degree of X at that time is 1. Okay, right? But then initially it was D, and observe that every time you delete, every time you right, so every time you delete a leaf, the degree of its unique neighbor decreases by 1, and that neighbor appears once in the prefer sequence. Okay, every time you delete a neighbor of a vertex, you add that vertex to the prefer sequence, right? And then we said that eventually by the end of the construction of the prefer sequence, or rather by at the time X is deleted or at the end of the prefer sequence, the degree of X must be 1, right? So during the construction of the prefer sequence, it must have dropped from D to 1, right? And therefore the number of times X was written in the prefer sequence is D minus 1. Yeah, cool. So that's a nice argument. So what I will do is, so what we'll do today is we'll kind of formally, recursively define the notion of a prefer sequence in a more formal manner, and then I'll leave this claim for you to prove by induction. Okay, so that should be an easy exercise for proofs by induction now. Raise your hand if you are in a you think you are in a position to prove this claim after, let's say, half an hour of thinking. Okay, so let's about half the class is comfortable proving this. So I'll leave it for you, but in any case, we are going to discuss it in the tutorial, right? So that's not super critical for us. It's just the observation that, right? So yeah, all we need is the fact that everything that does not appear in the prefer sequence is necessarily a leaf, right? And then the argument is the same if a vertex has degree 2 or more, right? So either this vertex itself is deleted during the construction of the prefer sequence, which means at that point of time its degree must have been 1, which means before that all its neighbors have been deleted, so which means this vertex must have appeared in the prefer sequence. Or the other possibility is this vertex survives till the end of the construction of the prefer sequence, in which case at that point of time its degree must be 1, and if initially its degree was more than 1, one of its neighbors at least must have been deleted, so therefore that vertex is going to appear in the prefer sequence. Awesome. Okay, so now let's try to construct the tree from this prefer sequence, and then we'll go to the formal definitions and so on. Right. Any ideas, any edges that you can already see in this tree, right? So this is some mysterious tree whose prefer sequence is this. We have already identified the leaf nodes of this tree. Can somebody identify some of the edges of the tree? Yes, Somil?
So we know the leaves, so we know that the minimal leaf, like the leaf with the smallest label, will be the first to be removed. So the first element of the sequence is connected to that minimal leaf.
Good. So
yeah, so we can try like so now it becomes kind of similar to the induction thing that we were doing. Like I think most of the proofs that we need will follow by just inducting by removing that leaf. And
yeah, you're right. So Somil's argument is, look, 3 is the leaf with the minimum label, so let's take that 3, and when we remove 3 we recorded a 1, which means 1 must be the neighbor of 3. Cool. So then what? How do you continue this argument? I mean, inductively, yes, what you said is right, but let's try to kind of iteratively construct the argument. Rishabh?
So after that, we look at the next smallest leaf, which is 4, and which gives you the edge 4, 5.
4, 5. Okay, cool. So continue.
Now from the thing we proved earlier with degree -1 being the number of appearances, you see that 5 now becomes a leaf.
Good. Nice observation. Yes. And
so now 5, 9 will be an edge.
5, 9 will be an edge. Okay. So let's pause for a moment and let's repeat this argument once again. Right. So 3 is the minimum leaf with the minimum label. So which is why, and this is the first entry of the prefer sequence. So 3 is connected to 1. Then what? So then look at the tree, look at the remaining tree, right? Its prefer sequence after deletion of 1, some tree remains, and its prefer sequence is 5979102. What is the minimum number which does not appear in the sequence? Well, it is 4. So that is a leaf of the remaining tree, and its neighbor must be 5. So that justifies these two edges. Now what remains? So after I delete 3 and 4 from the tree, whatever tree remains, it has the prefer sequence 979102. Okay, right? And so what is the minimum numbered leaf in that tree? It must be 5, right? Which means 5 is the neighbor of 9. Okay, Raise your hand if this argument is not clear. Why 5 is chosen and we have attached 9 to it and not 6? Raise your hand if this argument is not clear. Yeah, Sachit, is this not clear?
Yes, sir. Like 5 is attached to 9, that one.
Sorry?
Like 5 is attached to 9, that step is not clear.
That step is not clear. Okay, we'll do it once again. Don't worry. Yeah, we'll do it once again. Right. So, right. Okay. So 3 is attached to 1. I hope that is clear with everybody. And now what do we know, right? So whatever tree remains over here in the red circle, right? That is everything except this vertex 3 and the edge 3, 1. Its prefer sequence is 5979102. And its vertex set is what? Its vertex set is everything except 3. So its vertex set is 0, 1, 2, 4, 5, 6, 7, 8, 9. Sachit, are you with me up to this point?
Yes, sir.
So now this is 5979102 is the prefer sequence of some tree over this vertex set, right? Which is the minimum labeled leaf in that tree. Sachit?
0.
Sachit, what is the minimum labeled tree leaf of this tree?
0.
So 0 appears in the prefer sequence, right? Right. So a leaf cannot appear in the prefer sequence.
5.
Sorry?
5.
No, but Sachit, again, that's what I'm saying. 5 also appears in the prefer sequence.
4, sorry, sir. Sorry, I'm getting confused.
Yeah, 4. Okay, good. And its neighbor is?
And its neighbor will be 5.
5, exactly. Okay, so we know that, right? So now we know that 4 is a neighbor of 5, and let's continue our kind of backward construction of the prefer sequence. So whatever remains over here, whatever remains in the red circle is going to be a tree over the vertex set, right? So 4 is out of the vertex set. So it's going to be a tree over the vertex set 0, 1, 2, 5, 6, 7, 8, 9, and its prefer sequence is going to be this. Sachit, continue the argument. Sachit?
Sir, I'm still getting the confused. Can you explain? Like, I'm getting confused a bit.
Up to what point? So you agree that 4 is you said that 4 is a neighbor of 5, right?
Yes, sir. Yes, sir.
Right. So now whatever that tree is, right? I delete 4 also from that tree, and I get some tree which is enclosed in this red circle.
Yes, sir.
And its prefer sequence is 979102.
Yes, sir.
So now what? And its vertex set is this, because we removed 4 from the vertex set. Right? So given a prefer sequence and a vertex set, identify a leaf and continue the argument. What is the leaf of this tree in the red circle?
Like,
right? Sachit, anybody else? Right. So what is the minimum numbered vertex that does not appear in this sequence? That is 5. Right.
Okay,
so 5 must, yeah. So 5 must be a leaf of the tree in the red circle.
Yes, sir. Got it.
And its neighbor is what? Its neighbor is 9. Okay.
Yes,
so right. So let's try to shrink this circle now. Right. So the neighbor of 5 is 9. Let's continue. Right, and then what? So now we are looking at this tree. This tree, its vertex set is everything except 3, 4, 5, which means its vertex set is 0, 1, 2, 6, 7, 8, 9, and its prefer sequence is 79102. Sachit, one more step. If that's clear to you, what next?
So I'm still confused. Like I'm somehow forgetting the pattern again and again. Like I don't know.
Oh, I see. Okay. So every time you remove the smallest numbered vertex, right? So every time you conclude that the smallest numbered vertex which does not appear in your prefer sequence is a leaf, and its neighbor is the first entry of the prefer sequence. That's the pattern. Okay, the smallest number vertex which does not appear in your prefer sequence is a leaf, and its unique neighbor is the first entry of the prefer sequence. Okay. So what does the smallest neighbor? Yeah.
The smallest neighbor. Can you
Smallest,
repeat once again?
smallest labeled. Okay, let me just write it down. Smallest labeled vertex not appearing in the prefer sequence is a leaf, and its unique neighbor is the first entry of the prefer sequence. Right, so this is the pattern that we are using. That's all. Okay, and this is obvious from the way we define the prefer sequence. Right, so now do you want to continue, Sachin?
Can you tell again what do you mean by unique neighbor? Like smallest vertex not appearing, I got it right. Like last time it was
So
5.
it's a leaf, right? It's a leaf, which means it has just one neighbor, exactly one neighbor. And who is that? That is the first entry of the prefer sequence. Okay.
Okay, sir. No,
Yeah. So is the leaf in this? How do you continue this now?
like in this case, like we can't have 3, 4, and 5 are out of it.
Yeah, that's not even a vertex.
So it should be 1.
One appears in the prefer sequence.
6.
6, exactly. 6 does not appear over here, and its neighbor is
7.
7. Absolutely. Good.
Okay, thank you, sir. Sorry.
Is it clear now?
Yes, sir. Thank you. Sorry for.
No issues at all. No issues at all. I'm pretty sure it must not be clear to several people in the class. Okay, so the neighbor of 6 is 7. Somebody wants to continue? Right, so 6 is out of the vertex set. You are left with this prefer sequence. Now what?
So now 7 is the smallest. Is the smallest number not appearing in the prefer sequence. So it will be 9.
9, correct. Good. So 7 goes out of the vertex set. We know that the neighbor of 7 and 9 are neighbors. Now our tree has shrunk to something like this. Okay, continue. So this prefer sequence I need to change, right? So you are left with this 1, 0, 2.
Now 8 is the smallest.
8 is the smallest, yeah, and its neighbor is 1.
Yes, 1.
Good. Right. Next,
1 will be the smallest not appearing in the sequence.
And its neighbor is 0.
0.
Good. So 0, and your tree has shrunk to so what should I delete from the sequence? 1 should be deleted.
No, 0 we have to delete now.
No.
From the
vertex set. Vertex set. Yeah, go on.
Now 0 is the smallest not appearing appearing in the sequence.
0, 2. The sequence is 0, 2. What do you mean 0 is not is the smallest? 9 is the smallest, which does not appear.
Oh, yes. I thought we deleted deleted 0. Okay. So yeah, 9 is the one.
Good.
And
Good. So which means
its neighbor is 0.
Its neighbor is 0. Good. Right. So what survives is, so 9 goes out of the vertex set. You are left with 0 and 2. Right. And the tree looks something like this. Okay. Yeah, and 2 is left now. What now? Yeah, so your proof. Okay, so did I go wrong somewhere? Is there something else left in the prefer sequence? Right, so this is what we are left with as a prefer sequence. Something else is left, no? Zero, 1, 2 is left. 2 is somewhere over here. 3, 4, 5, 6, 7, 8, 9.
So I think you connected 9 to 0 instead of 2. Like I think you connected 1 to 0, right? Then you should have connected 9 to 2, I think.
Oh, I see. I see. And then 0 and 2 are neighbors.
Yes.
Oh, okay. Good. I see. So I think I forgot to remove an entry from the prefer sequence. Okay. So let's maybe undo a couple of steps then. Let's undo a couple of steps. I hope we are able to do that. Right. So up to this point, it was correct, right?
Yes, sir. I think so.
Yes, sir. I guess the last correct step was 8 to connecting 8 to 1. After that.
Okay, connecting 8 to 1 was the correct step, and it appeared over here. It happened over here, right?
Yes. Now we delete the 1.
Okay. So now your prefer sequence is just 0, 2. Good. Now your prefer sequence is 0, 2, and then so 1 is a leaf, and its unique neighbor is 0. Okay, good. I hope this works out nicely. 1 is a leaf, its unique neighbor is 0. So this is what is left in the tree. 1 is a leaf, its unique neighbor is 0, and now your prefer sequence is just 2. And your vertex set is 0 to 9. Right, and now what? Right, so now 0 is a leaf of the remaining tree, and its unique neighbor is 2.
Yes, sir.
Yeah. And now your tree, so this is right. So this is your remaining tree. Everything inside the red whatever curve, and its vertex set is obviously 9 and 2. And its prefer sequence is empty, which means it must just be a single edge. Right, so this is your tree. Okay, is it clear? Is it clear? Absolutely. Right, so maybe I'll give you some trivial problems to construct trees from sequences and vice versa, just for the sake of practice. I think even I'll have to practice it because I messed it up somewhere. But I hope the idea is clear at least. Okay, cool. Fine. So this is the way you construct a tree from a prefer sequence. Okay, so with all this intuition in mind, yeah, Arush?
Sir, how did you realize there was a mistake when you were doing it?
The reason was that see, every time the length of the prefer sequence has to be 2 less than the size of the vertex set, right? And at some point of time, I realized that the vertex set has size 2, but the prefer sequence has length 1. So that is some weird thing, which means I forgot to remove something from the prefer sequence sometime.
Okay, sir. Thank you. So I think it was that 0, sir.
Yeah. So
That's
I
why I
think I
got
forgot to
confused.
remove the 0. Exactly.
Yeah.
Right. So when I connected this 1, or what did I connect to 0 first? 9 I connected to 0, no? Or no, 1?
No, we connected 1 to 0 and then we forgot to delete the 0.
Correct. So we connected 1 to this 0 and then forgot to delete this 0. And so which is why we connected 9 to again to this 0 instead of to 2. Good. Yes. Yeah. So that was the mistake. Cool. So now that we have some, yes, Ramanuj.
Yes, sir. So this proof isn't really complete yet, right? Because
No, we have not even started with the proof. We are just developing intuition before we formally write the proof. We haven't even started the proof. Okay. We'll do that. Okay. So now that we have this intuition, let's kind of formally define the prefer sequence in a recursive manner, inductive manner. And then that inductive definition will be useful for us to prove that this function mapping a tree to a prefer sequence is in fact a bijection. Obviously, even that proof will go by induction. Okay, so let us formally define the notion of a prefer sequence. Definition of prefer sequence. Oh, by the way, I'm not sure whether you all noticed this color coding that I'm consistently using. I'm writing definitions in green, formal proofs in blue, claims in red, and everything else in black. And then I'm using the other colors as and when I need. Right. So I hope that helps. Okay. So what is the definition of a prefer sequence? Let S subset of n, right? N is not super important. All we want is some fixed ordering of the set S. Okay, but yeah, for convenience, we have just taken it to be n. Let S subset of n be a finite set with size of S greater than or equal to 2, right? So for the single vertex tree, we really don't define a prefer sequence. Okay, let T be a tree with vertex set S, right? So the prefer sequence of T is defined as follows, right? So this is an inductive definition, unlike an inductive proof. Shrimanti, I'll come to you. Let me finish this definition and then I'll come to you. Right. So how is this defined? If size of S, right? Yeah. So if size of S is equal to 2, then the prefer sequence is empty. Is the empty sequence. Right. So this is the inductive definition, size of S is greater than 2. What do? Let so let X be the minimum leaf of T and Y be the unique neighbor of X. Okay, so let T equal to S comma, let's say set of edges E, right? Let T prime be the tree Let T prime equal to, from S I am removing the leaf X, and from the edge set I am removing the edge XY. Right. So the Prufer sequence of T is then what? So then Prufer sequence of T is equal to the entry X followed by the Prufer sequence of T prime. Right, so if the size of the set is 2, which means the tree has just one edge, then we define its Prufer sequence to be the empty sequence. If size of S is greater than 2, what do? Let X be the minimum leaf of tree T, and Y be its unique neighbor of X. Now I am constructing a new tree. How am I constructing the new tree? From this original tree T, I am removing the vertex X and I am removing the edge XY, right? So that way you get a tree. And then I define the Prufer sequence of T to be X followed by the Prufer sequence of T prime. Right, so this is the way I'm inductively defining the Prufer sequence of a tree. Shrimanti?
Sir, like I'm saying that when we defined the previous Prufer sequence, there 3 was connected. We took 3 connected to 1 first, and then we removed 3. So we know that now the degree of 1 should become 2. So we did, so if like 1 had occurred only once, then it would have been a new leaf, right?
Correct. Correct. If this
Okay,
was the
so
unique occurrence of 1, then 1 would have immediately become a leaf after we deleted 3.
then we would have connected it to 5.
Correct.
Okay, okay.
Yeah. Okay. Somebody also had a question. Somebody else had raised their hand. Was it you, Vedant? Sachit. Okay, Sachit had raised. Sorry. Yeah, Sachit.
Yes, so like, shouldn't it be Y times Prufer sequence of?
Good. Sorry, my bad. Yeah, you record the neighbor. You don't record the leaf which you remove. Yeah, absolutely. Thanks, Sachit. Right. So Prufer sequence of T is Y appended to the, Y followed by the Prufer sequence of T prime. Okay. So now should we proceed with proving the result that right? So there is a one-to-one correspondence between the set of trees and the set of sequences. Right. So let me go to a new slide and state the theorem. Right. So let S subset of n be a finite set with size of S greater than or equal to 2. Right. So this is what we'll always assume. Okay. So let's denote the sequence by something. Let Z1, Z2 up to Z size of S minus 2 be any sequence of length size of S minus 2 having entries from S. Right? Obviously, it's a sequence, which means the entries can possibly repeat. So possibly with repetition. Okay, so this is the setup. You are given some sequence of size of S minus 2 of length size of S minus 2, where every entry comes from the finite set S. And now I want to claim that then there exists a unique tree T over the vertex set S whose prefer sequence is this sequence. Right, so if suppose we prove this theorem, what does this tell us? This tells us that the function which maps a tree to its prefer sequence is a bijection, and therefore counting the number of trees is same as counting the number of prefer sequence. The latter one is right, so every sequence of length size s minus 2 is the prefer sequence of exactly one tree. So therefore, and the number of prefer sequences is obviously size of s to the power size of s minus 2. Right, so remember that so if we prove this theorem, then you have the corollary, right? So the number of trees over a finite vertex set S is size of S to the power size of S minus 2. Right, so again remember, this S being a subset of N is not super critical. As long as you have you are working with some fixed order on the set S, everything is fine. Right, so which is why in this corollary I didn't say that S is a subset of N. S is any finite set. The number of trees over that finite set is size of S to the power size of S minus 2. Except that in order to define the prefer sequence, you will have to first fix an order over S if S is some arbitrary set. Okay, so should we try to prove it? Actually, the proof is not too hard. I mean, it looks like a big heavy hammer kind of a result, but the proof is, I mean, after all the intuition that we have developed so far, the proof is not too hard. Okay, so proof of theorem. Right, so this is not the proof of corollary. Corollary is kind of easy. Right, so how do we proceed? So let's go by induction on size of S. Remember that we are allowed to use induction on size of S because S is a finite set. Right, so if we were trying to prove something about possibly infinite sets of natural numbers, you just couldn't have used induction on size of S, right? That would not have been sufficient. Okay, so induction on size of S, base case is what? Base case is size of S equal to 2. Case is base case is size of S equal to 2, right? So what happens? So then right, the only sequence of length size of S minus 2 is the empty sequence, which is by definition the prefer sequence with of the only tree on S, of the only tree with vertex set S. Right, so I hope the induction, the base case is kind of trivial. So what is the induction hypothesis? Right, so for every, what is the induction hypothesis? For every S prime subset of N with size of S prime less than size of S, what do you have? And every sequence, well, here I'm stating it in the form of strong induction, but we really don't, you need to use strong induction, but doesn't hurt, so let me just state it that way. Every sequence, what do you call it? Z1 prime, Z2 prime up to Z size of S prime minus 2, there exists a unique tree on tree T prime on vertex set S prime whose prefer sequence is this. Z1 prime through Z prime S prime minus 2. Right, so this is the induction hypothesis. Now what is the induction step? Right, so how do we start the induction step? Okay, so we need to prove two things, right? So we are saying that there exists, right? So there are really two parts of this claim. There exists, and the second part is a unique tree, right? So let's first prove the there exists part, and then we'll prove the uniqueness part, right? So first part is existence. Right. So we want to prove there exists a tree. So this will give a proof by construction. So how do you construct a tree? Right. So remember the size of the sequence is size of S minus 2. So therefore there exists an element of S which does not appear in the sequence. Right. So since length of sequence Z1 through Z size S minus 2 is less than size of S, there exist elements of S which don't appear in the sequence. Let X be the minimum such element. Right? So now in the tree that we construct, we'll ensure that X is a leaf and its neighbor is Z1. Okay. So now what? Now we'll apply the induction hypothesis, right? So we'll apply the induction hypothesis on this sequence Z2 to Z size of S minus 2. Right, so X does not appear in this sequence Z2 to Z size of S minus 2, which means, so the sequence, right, so let S prime be equal to S minus X, right, remove X from the vertex set, and now Z2 to Z size S minus 2 is a sequence of length size of S prime minus 2, and its entries are all from S prime with entries from S prime. Right, so just check each and every statement that I'm writing, right? So X does not appear in this sequence at all. So which is why I said that, okay, even if I just forget this first element, right, the remaining sequence is not going to contain X, and therefore it's going to be a sequence over S minus X. And its length is going to be 2 less than the size of this set, S prime. Right, so therefore by induction hypothesis, there exists a unique tree T prime whose prefer sequence is this Z2 to Z size of S minus 2. Right, so this is what the induction hypothesis tells us. And now what? Now, right, and remember that Z1 is also an element of this set. Also, Z1 is not equal to X because X does not appear in the sequence, and right, so S prime is just S minus X. So also Z1 is in S prime. Okay, so now construct by adding vertex x to x and edge x z1 to t prime. Okay. Right, and now check. Now check. Right, so I'll kind of leave this step for you to figure out. Now check that the prefer sequence of t is precisely z1 z2 up to z size of s minus 2. Right, so all you need to prove is that x is the minimum leaf of the tree t. That's all. Okay. Okay, raise your hand if you are confident that you will be able to figure this out. Shrimanti, if that is a question, just lower it for now. I'll come back to you. Yeah. So raise your hand if you're confident that you will be able to check. You will be able to perform this check. Right. So I have exactly described the process that we did earlier, except that now I have used kind of explicitly written it down in words. Okay. Others, what is the difficulty? Could you? Where are you stuck? Could you just let me know? Also, Shrimanti, you had a question.
Yes, sir, I was asking. Yes, sir. So I was asking that we said here we are not using strong induction, right? We are using only induction.
Yeah.
So like we took S, the elements of S which do not appear in the sequence, and we took X as the smallest element. Now, sir, why did we remove Z1? What did we assume Z1 to be?
No, we did not remove. We removed Z1 from the prefer sequence, right? Because that's how we define the prefer sequence to be, right? Right. So this is our Z1 in our proof, and this is the remaining prefer sequence of T prime. Right. So from this prefer sequence, we know that there is a unique tree T prime, which has this prefer sequence. Now we are slightly modifying that tree to get a tree T whose prefer sequence is this whole thing.
Okay, sir, got it.
Okay. And that's exactly the way we did it earlier, right? The way we did it over here. Okay. So now uniqueness is also easy. Right. So suppose two trees, suppose trees T1, T2 over the vertex set S have the same prefer sequence. Let's say Z1 through Z size is minus 2. Right. So now we want to prove that T1 and T2 are in fact the same tree. Right. So now what do we have? So let X be the minimum element of S which does not appear in Z1 to Z size of S minus 2, right? And let, right, like before, let T prime be the unique tree over vertex set S prime equal to S minus X whose prefer sequence is Z2 to Z size of S minus 2. Right, so this again this is the same application of induction hypothesis. Right, so you reduce the length of the Prufer sequence, you reduce the vertex set, and by induction hypothesis you claim that there exists a unique tree whose Prufer sequence is this. That's what induction hypothesis allows you to do. Right, so now what? Now right, so we observe that right, so all elements of S that don't appear in the Prufer sequence Z1 through Z size of S minus 2 are leaves of both T1 and T2. Right, and this argument we have kind of informally seen earlier. Right, so given a Prufer sequence, right, that uniquely defines the leaf set. Right, so therefore T1 and T2 have the same leaf set. Right, and now because they have the same leaf set, so therefore X, right, so X in particular does not appear in the sequence, so X is the minimum leaf of both T1 and T2. Okay, so T1 and T2 agree on the leaf set. In particular, they agree on the identity of the minimum leaf. Right. So now X, the unique neighbor of X, the unique neighbor of X in both T1 and T2 is Z1. Right. Again, everything is by definition of the Prufer sequence. Right, and therefore, so now therefore, right, so in both T1 and T2, X, the unique neighbor of X is Z1, and now if I remove X and that vertex Z1, sorry, and that edge X Z1, whatever I'm left with is the unique tree T prime. Right, is everybody with me up to this point? Okay, raise your hand if you are not with me up to this point. Okay, cool. Right, so the unique, what did we say?
Sir, could you please explain the last step again?
Okay, yeah, sure. I'll explain the last couple of steps in fact. Right, so we agreed that all elements of S that don't appear in the Prufer sequence are leaves of the tree. Right, so they must be the leaves of, so that precise set of elements must be the set of leaves of both T1 and T2. So T1 and T2 have the same set of leaves. That's all we are saying. Okay, so now because they have the same set of leaves, they have the same minimum leaf. Okay,
so got it.
Yeah. So X is the minimum leaf, and by the definition of the Prufer sequence, in both T1 and T2, the unique neighbor of X must be Z1. Right? And
Yes,
now,
sir.
right, so on removing vertex X and edge XZ1 from both T1 and T2, we get the tree T prime. Why? Because on removing the vertex edge X and edge XZ1, in both cases we get some tree whose Prufer sequence is Z2 through Z size S minus 2. But then there exists a unique such tree. So therefore, in both cases, you must get that same tree T prime. Right? So therefore, right? So therefore, T1 is equal to T2. Questions? Maybe I'll wait for a minute or so. Okay. So should we move completely to some new kinds of graphs now? Because I didn't want to go into details of those kind of graphs. I just want you to be aware of the existence of such graphs and the fact that they have been kind of well studied, and you are going to encounter them in the future courses somewhere sometime. But that I will start only if everything that has been all the graph theory that I have covered so far is kind of yeah, is you are all comfortable with that. So should we proceed? Okay, fine. So yeah, I think I might end the lecture early. I don't know. Let's see. Okay, so what? Right. So now, so the topic for discussion for the rest of the class today is other kinds of graphs. Right. So however we define graphs, right? If you remember the first lecture of graph theory, we said that a graph is a pair, a set of vertices, a set of edges. The set of vertices is some finite set. The set of edges contains some subsets of the vertex set which are of size 2. Okay. So a perfectly reasonable another kind of graph is something called a multigraph. So what is a multigraph? Possibly more than one edge between two vertices. Right, so I'm not going to formally define these. I leave that task for you all. These are not super important as far as this course is concerned, but I just want you to be aware. Right, so a multigraph will look something like this. Right, let's say two edges from this. Right, and then there is just one edge. There is just one edge over here. Maybe there are three edges over here. Something like this. Right, so now you cannot define the edge set to be a collection of two subsets of the vertex set, right? Because this and this will really be the same vertex set. So you'll have to define it to be a multi-set or something like that. Or there are other ways to formally define it. I leave that for you to figure out. Right, and then lots of things kind of which hold for usual graphs also carry over for multigraphs. Right, so you can define walks in exactly the similar manner, except that when you define walk, you'll have to disambiguate and tell which edge you are taking. Right, so if I call these vertices A, B, C, D, E, right? So if this were a usual graph, I could have said that I could have talked of a walk of the form A, B, A, C, D, E or something like that. But now since there are multiple edges, it's not clear what does this walk even mean, right? So for concreteness, I'll have to tell, in this case for concreteness, I'll have to tell you that, okay, while going from A to B, I'm taking this edge, then for going from B to A, I'm taking that edge, and so on. Right, so I'll have to add more information to my walk to kind of completely define it. Okay, the notion of paths is, yeah.
No, sir. No.
Yeah, so the notion of paths is the same, a walk without a repeated vertex. Connectivity notion is exactly the same. Cycle notion slightly changes. In this case, you could have this, you could have A, right? So I need to call the edges. I need to give names to the edges also now, and I need to include those as a part of my description of a walk or cycle. So let's call this E1, E2, right? So I could say that my cycle is A, E1, B, E2, A. This is a cycle, but A, E1, B, E1, A is not a cycle. This is a cycle, not a cycle. Right. So what we would want is a closed walk in which no edge repeats essentially. Right. You could be going back and forth. Oh, sorry. No edge repeats, no vertex repeats, except for the first and the last vertex. Okay. So that is the notion of a cycle in a multigraph. What else? Right, so pretty much connectivity carries over, trees, spanning trees, all that stuff carries over in a natural manner. Not much of a difference over here. Okay, so yeah, I leave this multi-graph business with this kind of less than 5-minute discussion. There are another type of graphs that I want to introduce you all to is something called a directed graph. Directed graph, also called a digraph. Right, so what is a directed graph? A directed graph is one in which, right, so let me slightly formally define it, right? So it's a pair V and A, right? So V is again a usual a finite set called the vertex set, and now A, right? Earlier the set of edges was, so every edge was an unordered set of two vertices, right? So now here you are going to have an order, right? So A is going to be a subset of V cross V. Okay, so how will a diagram typically look like? You will have some vertex set, and you will have these kind of edges. You could have edges going back and forth. You could have edges going in only one direction, right? You could have a self loop kind of an edge, right? Because A is just a subset of V cross V, right? So A could contain elements of the form little v little v. That is allowed. Okay, so you could have something like this, right? Okay, so this is an example of a directed graph. Okay, again the notion of paths is analogous, except that you need to traverse the edge in the right direction. You cannot traverse it in the wrong direction, right? So in this graph, let's call this A, B, C, D, E, right? Right. So in this path, observe that there is a in this graph, observe that there is a path from A to D, but there is no path from D to A. Okay. So right. So directed path. Path which respects the edge direction. Edge directions. Path or even a walk. Or even cycle for that matter. Right. So observe that whether it's a multi-graph, whether it's a directed graph, some results kind of carry over, right? So if A, Shrimanti, once again, let me complete the sentence. If there is a path from A to B and there is a path from B to C, then there is a path from A to C. I can say the same thing about walks, right? The one thing that I cannot say is, which I could have said earlier, but now I cannot say in case of directed graphs, is if there is a path from A to B, then there is a path from B to A. That I cannot see. Okay, that is the only difference. Shrimanti, you had a question.
Sir, I wanted to just ask that in cycle, both edges and vertices should be different. But in case of paths, I mean, except the first and last vertex. And in case of paths or walks, we have the distinct vertices.
In case of paths, you have distinct vertices, which implies that the edges also must be distinct.
Yes.
Right? Sir. Yeah. And in case of walks, there is no such restriction. Vertices could be repeated, edges could be repeated, everything is possible.
And cycle, both should be distinct.
Yeah, cycle, except for the first and the last vertex, which kind of completes the cycle, everything should be distinct. Edges should be distinct, vertices should be distinct. Okay, so fine. Yeah. So,
Sir,
yeah.
Sir, here A to A is also a path in directed graph.
Sorry?
Means then we could have a we could have an edge from A to A.
Yeah, that is allowed because A is a subset of the set of arcs, right? So in the context of directed graphs, edges are usually called arcs. So the set of arcs is a subset of V cross V. So potentially it could contain an arc of the form A comma A.
Okay.
Okay. Yeah. Right. So now, right. So in case of usual, in case of undirected graphs, we had a notion of something called an acyclic graph, right? So graph which does not have a cycle, right? So similarly, there is a notion called a directed acyclic graph, also called a DAG, D-A-G, DAG, right? So let me just introduce it over here. Directed acyclic graph, also called a DAG, right? So it's a directed graph which does not contain cycle. Contain a directed cycle, right? So the undirected, if you forget the edges of the directions of the edges, your graph could perfectly contain cycles. But then if you remember if you are so if you right, so if you remember the directions of the edges, then there is no cycle, right? So your directed acyclic graph could look something like this. Right, so there is no, I hope there is no directed cycle over here. Yeah. So what will be a usual scenario in which you'll encounter a directed acyclic graph, right? Let's say, right, so I'm slightly going into algorithms, but that's fine. Let's say, yeah. Right, so let's say you're I don't know, making tea in the morning, let's say. Okay, so what do you do, right? Is that a good example, or is there okay, let's say you're making egg omelette, right? So there are several possible tasks, right? So you crack eggs, chop onions, right? Now I'm going to add edge if I want to, right? So I'm going to add edge from task T1 to task T2 if T1 should necessarily be done before T2, right? So now what? So now mix eggs with onions, right? So this has to be done after you crack eggs and after you chop your onions, right? And then you could add, right? So add salt, pepper, right? And then you fry, and so on, right? So typical recipe will look like something like a directed acyclic graph, right? So remember, if your recipe graph has a cycle, then you can never do that recipe, right? Okay, yeah. So just wanted to give you some informal example of where a directed acyclic graph kind of arises naturally. Okay, fine. So that's pretty much it for today. I'm ending the lecture like 9 minutes early, but that's fine. Any questions before we stop? Right. So don't ask questions after I stop recording. Okay. So this is an opportunity to ask questions, if any.
So I wanted to ask that when will we get our homework and quiz results?
Homework is almost done. Quiz, it's going to take at least a week, I think. But definitely before the next quiz. Don't worry about it. Okay.
Okay.
Yeah. Homework is almost done. I hope the TS published the grades by today. Okay, cool. So if there is nothing else, then that's it for today. Wish you all the best for your remaining exams, and then we are going to meet on Saturday, right? Saturday morning we are meeting for the next lecture, and immediately after the lecture we are going to have a tutorial session. In the meantime, I'll add more problems to a tutorial session maybe. And on Saturday, yeah, so especially for those who are not attending right now, Saturday onwards we are going to start something completely new, which has nothing to do with graph theory. Okay, so if you want to catch up and start attending, that would be an excellent opportunity to do so. All right, so chalo then. Bye bye. That's all for today.